Okay, so let's look at some uses of this posterior distribution. So on this slide, I give two very simple examples of something we can do with the posterior of W. One is we can give probabilities. We can ask questions like, is the ith dimension of W positive or negative? And the reason why this would be important is that the ith dimension of W says that by increasing the ith dimension of X, we increase the expected output, whereas if Wi is negative, by increasing the ith dimension of X, we decrease the expected output. So this tells us how X relates to Y, and so this could be very important for practical purposes. Or can we confidently say that Wi is non-zero? And so all of these can be calculated using the marginal distribution on the ith dimension of W, which under the posterior is just a univariate Gaussian with mean equal to mu I, so the ith dimension of the mean, and variance equal to the ith diagonal element of the covariance matrix sigma. So this is something that we can show. And we can use this to characterize what we think the true value of Wi is, whether it's positive, whether we're confident that it's positive, whether we're confident that it's negative, or whether we can't even say whether it's non-zero. Also, we can ask questions like, how do the ith and jth dimension relate? So again, we can calculate the marginal distribution of the entire vector W by looking at the probability distribution restricted to the ith and jth dimensions. That's also can be shown to be a multivariate Gaussian, where the mean is simply the corresponding dimensions of the mean vector, and the covariance is the submatrix formed by taking the corresponding dimensions from the matrix. So these are things that we can calculate in order to understand what we think the values of the regression coefficient vector W's will take and how they relate to the covariates X. But also important is, and perhaps more important, which I want to discuss next, is the procedure of predicting new data given the old data. So we can use the posterior to help us make predictions for new data. So let's look at how we can make predictions for new data using Bayesian linear regression. So let's recall that we have a new pair, x0, y0, where x0 is the measured covariates, so we get x0, and we want to use x0 to now somehow predict the unknown response variable y0. So we saw how using the least squares of the ridge regression solutions, which correspond to the maximum likelihood, or the MAP solutions, what we simply do is say that we believe y0 is approximately equal to the dot product between x0 and either the least squares solution or the ridge regression solution. In both cases, we have a point estimate of W, and so we give a point estimate of our prediction with no uncertainty about what we think y0 is. So with Bayes' rule, we can make probabilistic statements about y0. What we want to calculate is a probability distribution on y0 given x0 and given the previously observed data. So this is the probability that we're interested in calculating. And so how can we actually calculate this probability? Well, we can represent that as a marginal probability over the unknown coefficient vector W. So we include W in a joint distribution and then immediately integrate it out to get the marginal distribution. And then given this joint distribution, we can represent it as a conditional distribution on y0 given W and given all of the observed data times this conditional distribution on W given all of the observed data. So we can factorize this joint distribution into the product of these two conditional distributions. This is just simple manipulations of probabilities. However, notice first that conditional independence here lets us say that the probability of y0 given the vector W given the covariance x naught and given all of the previous observations, is just the probability of y naught given w and x naught. Why? Because of our conditional independence assumption. So our assumption of how y is generated is that if you tell me the corresponding x naught and if you tell me the regression coefficient vector w, I have all of the information necessary to define the probability distribution on y naught. I don't need to take into consideration any other data. It's simply a Gaussian with mean equal to the dot product between x naught and w and variance equal to sigma squared. So that's the likelihood assumption that we make. And also, the probability of w given y and given x and given also x naught can be shown to be conditionally independent of x naught. So if you tell me x naught but you don't tell me y naught, then I have no extra information in order to update my probability of w above and beyond y and x. And so this distribution is equal to the probability of w given y and given x, which we observe is the posterior probability distribution. So both of these distributions are things that we know. The likelihood distribution, so this distribution is inserted here, is the likelihood. By the definition of the model, we can write that. And this distribution is replaced by the posterior distribution because of the conditional independence. And we've already discussed how we can calculate that for the linear regression problem. So this has a name. It's called the predictive distribution. So we're predicting new data given old data. And we represent the predictive distribution as a marginal over the likelihood of the new data given model variables times the posterior distribution of those model variables given the old data. And so intuitively what we're doing is we're evaluating the likelihood of something new for a particular w, for a particular model variable w, and then we're weighting that particular model variable by our current belief of what we think is going on with w as represented in our posterior distribution. We then sum all of those possible weighted models together. In this case, because there's an infinite number, a continuous number of possible vectors w, we're integrating. So we integrate over all possible model vectors w, and we're essentially removing all of the uncertainty of w in forming our predictive distribution. Okay, so let's look at predicting new data for the linear regression model. So again, we have the model of the new data given the model variable is a Gaussian like this with mean and covariance defined to be this. And by Bayes' rule, we know that the posterior distribution of the regression coefficient vector given y and given x is a multivariate Gaussian with mean mu and covariance sigma, where I've shown how to calculate those on a previous slide. So I won't work through the integral, but what we can show by calculating this integral using the Gaussian representations for these distributions is that the predictive distribution of y naught given x naught given y and given x is also a Gaussian with mean mu naught and variance sigma naught squared, where the mean is equal to x naught, the dot product between x naught and the posterior mean of w, and the variance is equal to the noise variance of the model. This is the noise from the likelihood, which we can't ever eliminate, plus some additional variance, which is equal to the product of x naught with the matrix sigma. So notice that with this predictive distribution, what we're doing is we're saying that our mean of the Gaussian, of our predictive Gaussian, is equal to the map prediction, because remember that we showed how the mean of the posterior is equal to the map solution. And so our mean, the mean of our predictive distribution is the map prediction, the point estimate we would make under map. But now we have this additional variance, which is used to give us a sense of how confident we are in what W is, which we couldn't have before because we used a point estimate to solve for it. Whereas now we have the posterior distribution of W, and so our uncertainty of W is contained in this distribution, and we can then use that uncertainty to propagate it forward to the predictive distribution.